Hey everyone, welcome back to Everything is Relative with me, Mr. K. Today we're going to be looking at Cambridge A-level physics again, and we're going to be doing some topical past paper questions from the Papa Cambridge website on the topic of alternating currents. And today we'll look at questions 316 to question 323. And as always, I'll leave a link to this website in the description down below, and you can use these questions, you can download them and use them to help you prepare for your final exam. And in doing these solutions, hopefully the topic and the questions themselves become a little clearer than they do by just looking at a mark scheme. And so the first question we have is, again, the question numbers are not very clear, so I'll write them out again. 316, the subject code is 9702. This question comes from the summer 2021 exam, so May-June 2021. This is question paper 4, variant 2, and question number 10 from that paper. And we are told that by reference to the heating effect, explain what is meant by the root mean square value of an alternating current. And so you may have or should have seen this kind of definition at some point, but the definition linking the root mean square value to the heating effect. So what do we know about the value of, so the RMS value of alternating current is that value of alternating current. So it is a single value. Root mean square is the peak value divided by the square root of 2. The value of the alternating current that will produce, or I should say that produces the same heating effect as direct current of the same value. So what does that mean? So it's that value of the alternating current that will produce the same heating effect as the direct current of the same value. So what this means is that if I calculate an RMS current of 2 amperes, it will produce the same amount of heating, it will produce the same power across a resistor as a direct current of 2 amperes would. That's basically how you can explain what root mean square value of current or voltage, what it means in terms of the heating effect. We are then told that the variations with time t of two currents I1 and I2 are shown in the figures below. So we have a nice sinusoidal current, and then we have a more block-shaped current. So not sinusoidal at all. It's a value of 2 and then goes to a value of -2 and then jumps back to a value of 2. So it's either 2 or -2. It doesn't take any other values in between. And we are then told to use figure 10.1 to determine the peak value and the RMS value of current I1. Well, I1 is a nice sinusoidal alternating current like we are used to. And let me try and first figure out what the RMS value is going to be. Now, I'm just going to derive what the RMS value is. Just quickly, you don't need to do this, but to show you why the RMS value is such. So the RMS value is the average of the squared values of the current. And this is the square root. Now, if you remember, current as a function of time, I is equal to the peak current times sine omega t, where omega is the angular frequency. And so this is the square root of I naught squared sine squared omega t. And so actually this is the average of this value. And so what this becomes is I naught divided by the square root of 2. So the average of sine squared will be 1. So sine squared can, or half rather. And sine squared can vary between 0 and 1. There won't be any negative values for sine squared, and so the average value of sine squared will be a half. Between 0 and 1 would be the middle value, which is a half. and the square root of I naught squared is simply I naught, and hence we get that IRMS is the peak current I naught divided by root 2. So what is the peak value? Well, we can read the peak value off from the graph. So the peak value is the maximum value in either direction, it doesn't matter, and that's 2.6 amperes. We simply need to read it off. We don't even need to do any calculation. The RMS value is 2.6 divided by the square root of 2, which will give me 1.8 amperes. Again, it took me much longer than I needed to, but I just wanted to show you where the RMS value I naught over root 2 comes from. Next, we are told to use figure 10.2 in this case to determine the peak value and the RMS value of the current I2. Peak is maximum. Peak is easily readable off the graph. I can see that it's 2 amperes. And so for the block-shaped alternating current that we have, not exactly alternating current, but it's changing direction at least, the peak value is 2. Now the RMS value, now this might be a bit tricky. Again, I said RMS value is the square root of the average values of I squared. So what is the average value of I squared? Well, the average value, so if I square this graph, then everything lies between 4 and 0. If 2 squared is 4, minus 2 squared is also 4, 0 squared is 0. And so if I square this graph and I draw a graph of I squared versus t, what I'll have is the same block shape, but I will have it always above the x-axis. And so the average of I squared will be 2. And because the average of between 0 and 4 will be 2, and so the average value for I squared is 2, and so this is the square root of 2 squared, which is simply 2. And so the RMS value turns out to be the same as the peak value. So be very careful. We have to remember what the definition of RMS is when we are working with anything that's not completely or not sinusoidal. Remember, an RMS quantity is a statistical quantity. And so it works nicely for a sinusoidal current that we say I naught over root 2, but it's not always the true case. In part C, we are told that the variation with time of the voltage supply to a house is given by the expression V is equal to 240 sine kt, whereas V is in volts, T is in seconds, and K is a constant with unit radians per second. The frequency of the supply voltage is 50 Hertz, and we want to find K to two significant figures. So the first thing we do is write it in standard form. V is V naught sine omega t. Because that way we can immediately read off that V naught is 240 volts, and omega is this thing K. So they ask us to find K to two significant figures, where K is simply omega. What is omega? We remember omega, the angular frequency is 2 pi times the frequency. The frequency is given, so this is simply 2 pi times 50. You aren't going to leave your answers in terms of pi because the answers are wanted specifically in radians per second. And so I get 314 radians per second, but I need to keep my answer to two significant figures. So that's 310 radians per second. We're then told that this supply voltage is applied to a heater, and the mean power of the heater is 3.2 kilowatts, and we're asked to calculate the resistance of the heater. Now remember, power is the RMS voltage squared divided by R. Whenever you're calculating the power, use the regular equations for power and use the RMS values for V and I if they come up in the equation. Now, if I don't have the RMS value for voltage, but I do have the peak value, 240 volts, V naught. So I can change the RMS and replace it with V naught, where RMS is V naught over root 2. So this V RMS squared becomes V naught squared over 2. So it's V naught squared over 2R, which means that I can rearrange this and solve for the resistance. The resistance becomes V naught squared over 2P. And this is the peak voltage, 240 squared, divided by 2 times the power, which is 3,200 watts, 3.2 kilowatts. And I get this to be 9 ohms. And so the resistance here is 9 ohms. So remember, when calculating the power in for alternating current, use the irregular equations for power, but use the RMS values. If you don't have the RMS values, put in the peak values. Well, but if you know one, technically you do know the other. So that was an interesting question, and altogether the question was worth 8 marks. The next question is number 317. And this is from the winter 2021 exams, so November 2021. It's question paper 4, variant 1, and question 9 from that paper. We are told to state by reference to the power dissipated in a resistor what is meant by the root mean square value of an alternating voltage. So similar to the previous question, however, they're asking us to state by reference to the power dissipated and not necessarily the heat transferred, and for the alternating voltage, not the alternating current. So it changes very slightly. So the RMS voltage is that value of the alternating voltage that produces the same, I'm going to use power now instead of heating effect, alternating voltage that produces the same power in a resistor. We're talking about specifically in a resistor now. So the power dissipated in the resistor is the same as a constant or DC voltage or direct voltage that has the same value. What this means is if we had an AC potential difference across a resistor of 3 volts, and we had, or an RMS voltage across the resistor rather of 3 volts, and a direct voltage of 3 volts, that would produce the same power in the resistor. So that's how we would explain what alternating current and alternating voltage is with respect to power or heating effect, etc. So it's the value of the alternating voltage that produces the same power in a resistor as a constant voltage of the same value. Next, we are told that a coil is rotating freely on frictionless bearings at constant speed in a uniform magnetic field. This rotation causes an induced alternating electromotive force across the open terminals of the coil. The induced EMF has RMS value 12 volts and frequency 50 Hz, and the speed of rotation of the coil is now doubled. State and explain with reference to the principles of electromagnetic induction the effect of the increased speed of rotation on the RMS value of the induced EMF. Okay, so be very prepared to see questions that will bring in magnetic fields, if not combine magnetic fields and alternating currents altogether. We don't really do transformers, so that may strengthen the case that magnetic fields and alternating currents be separated in the exam. But here's a question where you need to understand magnetic fields and understand alternating currents. So what happens if we increase the speed of rotation of this coil inside the magnetic field? Well, the reason a current is, or an EMF is being induced in the coil is because the coil is moving relative to the magnetic field. But what we know is that the induced EMF, or call it E, is proportional to the rate at which flux lines are being cut. So proportional to, I can even say delta phi, delta t. I don't really have to put the n there. N delta phi, delta t. And so the coil is remaining the same, but if it starts rotating faster, then more phis are being cut every second. There are more lines of flux being cut every second by the coil. It's moving through the magnetic field faster. And so the EMF that's induced is greater. So I need to write this in words. So how do I write this in words? So I need to say that the rate, now the word rate is very important here because I have something, delta something by delta t. Now the rate at which lines of magnetic flux or magnetic field lines or magnetic flux lines, the rate at which magnetic flux lines are being cut doubles. And so I can say, hence, the induced EMF doubles. So I can actually quantify how much the EMF is going to increase by. If I double the rate of flux lines being cut, I double the EMF that's produced. Okay, because they specifically say the speed of rotation of the coil is now doubled. And so we can actually quantify what this increase in speed will do to the EMF. It'll double the EMF. Now the next question says, on figure 9.1, sketch the variation with time of the induced EMF E across the terminals of the coil at the increased speed of rotation, and your line should extend from t is equal to 0 to t is equal to 20 milliseconds, assuming that E is equal to 0 when t is equal to 0. So I need to draw this alternating potential difference, this alternating EMF, induced EMF, across the coil as the coil is now rotating with its increased speed of rotation. So I'm going to draw something sinusoidal. But if I have to sketch a sinusoidal graph, I need to know some things. I need to know the peak values, and I need to know the period. So the peak values, well, let's first find the period actually, because the frequency I've been told is 100 Hertz. Well, I've told the frequency is initially 50 Hertz. And if I double the rate of rotation, then the coil is moving at 100 cycles per second. So 100 Hertz for the increased speed of rotation. 50 times 2 is 100. The period is 1 over the frequency, which means it's 1 over 100, which means that, and this is in seconds, so I'm going to skip a few steps and I'm going to write this as 10 milliseconds, as it becomes 0.01 seconds, so that's 10 milliseconds, since the time axis here is measured in milliseconds. So now I know the period of the sine wave, so I can at least tell what the shape of the sine wave is going to look horizontally. Vertically, though, I want to know how squashed or pulled out the sine wave is going to be. So I need to know the peak values of the voltage, the induced EMF. And so V0 is equal to, well, root 2 times the RMS, EMF. And the RMS EMF is 12 volts initially. It's obviously now doubled because we said the EMF doubles when the rotation doubles. So it's 2 times 12, it's now 24. So it's the square root of 2 times the new EMF, the new RMS EMF, 24 volts. And so this becomes 34 volts. So now I know the peak values of the voltage, and I also know the period, and I also know that E is 0 when t is 0. That's the first point that I can plot there. The peak value is 34, and the period is 10 milliseconds. So I must have one complete cycle in 10 milliseconds. And this means that I need to reach, I'm also going to pass through the horizontal, the time axis at halfway through the period, because I'm going to have one cycle above the x-axis and one below, and the peak value is 34, and so it's going to be here. And again, we're going to do the same thing, negative 34 and 34 again, and we're going to repeat this pattern because they did say our graph should extend from 0 to 20 milliseconds, so we're going to have 2 cycles. And so we can just use symmetry to plot the rest of the points. Again, you're going to make sure you do this accurately with a pencil, and your drawing is going to be a lot better than mine. Mine is not going to look very sinusoidal with this pen. But as you can see, it's definitely a curve shape. It's definitely got a period of 10 milliseconds because that's one complete cycle within 10 milliseconds, but the graph needs to continue. And so it should be a symmetrical shape about t is equal to 10 milliseconds and should have both positive and negative peaks. So you can see I have a sinusoidal curve, not drawn very well, but again, with a pencil, you draw this a lot better. You'd sketch this a lot better. So when drawing a sinusoidal graph for alternating current or for anything, I need to be able to find the peak values, and I need to find the period. If I have those, I can sketch it quite easily. And so this was a fair amount of work for 3 marks. So it would have taken you a good few minutes to get all this information and then sketch this graph in one go without lifting your pencil off the paper. Or at least trying not to lift your pencil off the paper. It's going to be important that you get the shape as fluid as possible. And so that question was worth 3 marks. Now the next question says, that we should state and explain the effect on the motion of the coil in B. So this coil where the speed of rotation is doubled, of connecting a load resistor across its terminal. So what happens if this coil is rotating freely? It's rotating at a constant frequency. There's no external force driving it, and suddenly we connect a load resistor across its terminals. What happens to the, specifically what happens to the motion of the coil? Okay, so when the coil is moving, there's an EMF induced in the coil, and hence the current induced in the coil. But if we connect a resistor across the coil, then the current is going to flow into the coil. So the current in the resistor dissipates or uses or dissipates energy. But where does that energy come from? Well, that original energy comes from the coil rotating in the magnetic field. There isn't anything else moving, but the coil is moving. So if the resistor is dissipating energy, it's taking some energy. That energy must come from somewhere. And that energy comes from the rotation of the coil. So I can say the energy comes from the coil's rotation. So what happens to the motion of the coil? Well, the coil must stop rotating. It can't continue rotating because then we would have infinite energy. It's continuing to rotate at constant speed whilst the resistor is constantly dissipating energy per second. That would mean infinite energy. So the coil will eventually stop rotating. And so if a resistor is added into the circuit, then the coil will eventually have to stop rotating unless we add some sort of chemical energy that we can use to convert to kinetic energy to spin the coil. But we don't have that in this case, so the coil will eventually stop rotating. And so that's another common type of question about how a generator works, but not directly, but how a coil would behave if we place it in a magnetic field. And so that question was 9 marks. It was an interesting question, and you need to be able to sketch graphs. And so calculating frequencies and periods and peak values are very important. The next question is number 319. And this question comes from the March 2019 exam. It comes from question paper 4, variant 2, and this is question number 8 from that paper. We're told that a horseshoe magnet is placed on a top-hand balance and a rigid copper wire is fixed between the poles of the magnet, as illustrated in the figure. The wire is clamped at ends A and B, and a direct current is switched on the wire, and the reading on the balance is seen to decrease. State and explain the direction of the force on the wire. Now, whenever you're talking about forces, always talk about forces on an object. That always makes it clear to the marker what you're referring to. So how do I know which direction the force on the wire is acting in? Well, I could use Fleming's left-hand rule. But the problem is I don't know the direction of the current, so I couldn't tell the force on the wire. So there must be another way to tell the force on the wire. Well, there is, because the reading on the balance is seen to decrease. So how does that help me tell what's going to happen in the wire? Well, let's write this down. Let's write it down and try to make sense of what this means. The balance reading decreases. What does this mean? If the balance reading decreases, what's on the balance? The magnet's on the balance. So the force on the magnet is upwards. If the magnet suddenly gets lighter, quote unquote lighter, then the force on the magnet must be upward to make the balance reading decrease. But that's the force that the magnet's feeling. But if we remember Newton's third law, remember, just as there's a force on the wire due to the magnetic field, there'll be a force on the magnet. So by Newton's third law, the force on the wire must be in the opposite direction, which is downward. So I'll say the force on the wire is downwards. So the force on the magnet is upward because the balance reading decreases. And by Newton's third law, that means the force on the wire must be downward. Remember, the forces must be equal in magnitude in opposite direction. Hence the reason why the force on the wire is downward. Aha, this now tells us the information that we didn't have before. We know the direction of the field lines, we know the direction of the force on the wire, and you can imagine what the next question is going to be exactly. Can you tell us the current in the wire? Well, now it's quite easy. I know that the field lines are pointing from north to south, so I use in Fleming's left-hand rule, my index finger is going to point in the direction of the field lines. My thumb is going to point downwards, and so my current, which is my middle finger, is going to point from B to A. And so how do I explain this in words? How do I qualify this? Well, I'm going to use Fleming's. Always write it down. If you can't remember how to spell Fleming, you can say the left-hand rule. I'm sure that's fine. But I'm going to say using Fleming's left-hand rule, which is enough to say you don't have to talk about the different fingers and different directions. You can simply say the current flows from B to A. So we use Fleming's left-hand rule because we now know two of the three things. We know the force and we know the direction of the field lines, so we can easily tell the current. If you know two of the three things, Fleming's left-hand rule can be used to find the direction of the third, provided they're all at right angles, which they usually are. Okay, next question is a little bit tricky. They tell us that a direct current of 4.6 amperes on the wire causes the reading on the balance to change by 4.5 times 10 to the minus 3 newtons. The direct current is now replaced by an alternating current of frequency 40 hertz and RMS value 4.6 amperes. Now on the axis of figure 8.2, we want to sketch a graph to show the change in the balance reading over a time of 50 milliseconds. Okay, this is a bit of a tricky one. So when I have an RMS value of 4.6 amperes of current, I'm going to get the balance reading change by 4.5 times 10 to the minus 3 newtons. So that's almost like an RMS force, if you will, because force, remember, is proportional to the current. Force is equal to Wilson, BIL sine theta. And everything else is remaining constant besides the current. It's only the current that's changing. It's changing sinusoidally. So guess what? The force is going to change sinusoidally as well. And so if I would think of the force as being alternating, then the RMS force would be 4.5 times 10 to the minus 3 newtons. That's a change in the balance reading. That's why I'm calling F, the thing that I'm plotting on the y-axis. Which means the peak force, if you will, I'll call it F naught, is root 2 times this value, which is 6.4 times 10 to the minus 3 newtons. So when the current is a maximum, the force will be a maximum and it will be this value. Now that gives me the peak value that I can plot on the graph, but remember, like I said, if I'm plotting a sine graph, I also need to know the period. And we're asked to show the change in the balance reading for the 50 milliseconds, so the entire graph paper. Now period is 1 over the frequency. And I'm given the frequency, so that's 1 over 40. And this is 0.025 seconds or 25 milliseconds, since I'm given milliseconds on the horizontal axis. Well, now it's actually not too bad to draw. So I know that here I'm going to have 6.4, and I'm going to have to look for 6.4 on the negative side. It's negative 6.4 newtons. And I also know that the period is 25 milliseconds. And so one complete cycle happens in 25 milliseconds. And so half of that will be 12 and a half. And halfway between there, 6 and a quarter-ish. Again, you will do this in pencil, you do it accurately, and you'll make sure that your points are in the correct places. I'm doing it a little bit haphazardly. But essentially you would have to measure these out, and you would see that it would be . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . will give you values that would look something like what I'm drawing. Okay, I haven't actually measured these values out here, but what I would do is I would now plot or sketch the shape of the sine curve, making sure that when the current is 0, the force is 0. And one complete cycle happens in 25 milliseconds, which means the period is 25 milliseconds. But I'm asked to do it for the first 50 milliseconds, so I'm going to have 2 cycles. But again, for this graph, I haven't really measured it very accurately, but you will. And when you sketch it, you'll get a nice sinusoidal curve where the peaks on the positive side are equal to the peaks on the negative side, and the period is consistent and it's a curve. It shouldn't look like jagged lines. It shouldn't look like straight jagged lines, like triangular in shape. It should look sinusoidal because as the current increases or current changes sinusoidally, so too will the force on the magnet. So you'll notice that the force on the magnet will change, and so the balance reading will change as well. So this is an interesting question. We've never heard of things called RMS force, etc. before, but we should know there's a relationship between force and current. And so we have to manipulate our mathematics in order to sketch a graph of the changing force with changing time. And so that question is worth 3 marks, but I guess it would take a little bit of working as well, a little bit of thinking outside the box. And so the total for that question was 8 marks. The next question is number 320. And this comes from the winter 2019 exam. It's question paper 4, variant 2, and question number 11 from that paper. We're told firstly to state Faraday's law of electromagnetic induction. So here's some more of magnetic fields coming through. And the induced EMF is directly, again, you should be studying magnetic fields before studying this subject, this topic rather. The induced EMF is directly proportional to the rate of change. Remember, rate of change is very important. To the rate of change of magnetic flux linkage. That's good enough for the definition or the statement of Faraday's law of electromagnetic induction. If you are struggling to remember the wording, remember that the EMF E is equal to minus delta n phi by delta t. And you can sort of infer what the statement for Faraday's law will be by looking at that equation. The induced EMF, which is E in this case, is directly proportional to the rate of change of magnetic flux linkage minus delta n phi by delta t. And so that's Faraday's law of electromagnetic induction. We're then told that a small solenoid has a solenoid S rather has a small coil placed near to one of its ends, as shown in the figure. So we have a solenoid S and a smaller coil C with 63 turns and a diameter of 3.6 times 10 to the minus 2 meters. We're then just told that the coil C has a circular cross-section of diameter 3.6 times 10 to the minus 2 meters and contains 63 turns of wire. The solenoid S produces a uniform magnetic field of flux density B in Teslas in the region of the coil C, which is given by an expression 9.4 times 10 to the minus 4 times I, where I is the current in amperes in the solenoid S. The variation with the time t of the current I in the solenoid is shown in figure 11.2. A lot of information given here. We are told to state 2 times at which there is no electromotive force induced in coil C. Wow, so what's happening? There's a current in solenoid S. Nothing's really happening in coil C, but the current in S produces a magnetic field. The magnetic field cuts the coil C and induces an EMF in coil C. That's what's happening. There's a current in S that's inducing a current in C. And the current in C is given by 9.4 times 10 to the minus 4I, where I is the current in the solenoid S. So we are told that the variation with the time of the current in solenoid S is given in this figure, and we want to know when the electromotive force induced in C will not exist. Well, the electromotive force induced, the EMF induced in C is proportional to the rate at which the magnetic field is changing. which means the EMF is proportional to the rate at which the current is changing, because the magnetic field is proportional to the current. There's a constant times the current, so B is proportional to I. So I need to know when delta I by delta T is going to be 0. That means E is going to be 0. So I don't want the times in which the current is 0, but I want the times in which the current is not changing. The rate of change of current is 0. And that happens when the gradient of the sinusoidal curve is 0. Well, we know for a graph like this that the gradient is 0 at the peaks and the troughs. So if I draw a tangent line to this graph at any point, that tangent has 0 gradient at the peaks and at the trough. So I have to mention any two times where the graph is at a peak or where the graph is at a trough. And I can see there's a peak at T1 and a trough at T3. So I can simply say T1 and T3. I could also say T5 and T7, or any two of those values actually, because there's no electromotive force when there's no change in current. When the current reaches a maximum or minimum value, momentarily it stops, and hence there's no electromotive force induced in the smaller coil. Next, we are asked to state two times at which the induced EMF in coil C is a maximum, but with opposite polarities. So again, the induced EMF is going to be given by the rate at which the sine graph is changing. But now they want the maximum. They don't want 0, but they want the maximum. So the maximum is going to be the maximum gradient. But they must be opposite polarities. So in one case, if I look at this graph, I can see the maximum gradient occurs when the graph is passing through the time axis, because that's the point where the graph is the steepest. But I need one time where the graph is going down and another time where the graph is going up, because that will be different signs. So in this case, the gradient is negative. In the other case, the gradient is positive. So opposite polarities, since the EMF is proportional to the rate of change, proportional to the gradient. So I can simply say T2 and T4. I can also say T4 and T6 up and down through the time axis. And so they must be opposite polarities, but they must be a maximum. And so the induced EMF is a maximum when the current is 0. As you can see, the current is changing direction. And so that's the biggest change in current, hence the biggest induced EMF. Now we are told that the alternating current in solenoid S in B is replaced by a constant current of 5 amperes. And we want to find the average EMF induced in coil C when the current in solenoid S is reversed in a time of 6 milliseconds. What that means is we have a constant current of 5 amperes, and then we change the direction of the current. We have a direct current of 5 amperes, swap the terminals, and make the final current minus 5 amperes. So that's what we talk about when we say swapping. And we want to find the EMF that's induced in C when we flip the current in solenoid S. So it's moving in one direction and suddenly moves in the other direction. Magnitude 5 and then magnitude minus 5. And this whole process takes 6 milliseconds. So the average EMF induced, delta E, is N delta phi by delta T. And remember delta phi, or rather let's just say phi, N phi, the flux linkage is B times the cross-sectional area A times the number of turns in the coil N. And so that's what N delta phi is. It's delta B A N, since the area and the number of turns remain constant. So we can write this as 9.4 times 10 to the minus 4. That's part of B. Times the cross-sectional area. I'm going to leave the current for the last part, which is part of B as well. And this is 10 to the minus 4. Now the cross-sectional area is pi times the radius squared. So that's pi. We aren't given the radius, but we're given the diameter, 3.6 times 10 to the minus 2 meters. So I'm going to write the radius as 1.8 times 10 to the minus 2 meters squared, since it's a circular coil, circular area, multiplied by N, multiplied by the change in I, the change in the current, divided by the change in the time. So let me put some values into this for those that are missing. That's 9.4 times 10 to the minus 4 multiplied by pi times 1.8 times 10 to the minus 2 squared. Now the number of turns in the coil is 63. The change in current, the final current, we can say is 5 amperes minus 5 amperes. So again, I'm just choosing the value so that I get a positive number. Doesn't really matter. So 5 minus 5. Since the current is in one moment going in one direction and then we flip it, so it's in the other direction, minus 5 amperes. And in the time of 6 times 10 to the minus 3 seconds. So a lot of work goes into this. But what I get is the EMF that's induced is 0.1 volts. So when asked to find the average in EMF induced when a current is switched in a certain time, take that value of the current, subtract it from the negative of that value, which is basically adding it to itself. It's minus minus becomes plus, and divided by the time, and you get the, if you get the magnetic flux in your numerator or the magnetic flux linkage in your numerator, then what you get is the induced EMF. So a little bit of working in that problem, but I've seen a few questions that are very similar to this. So overall 7 marks, but fair amount of time, especially for the last question. Unless you've seen one before, in that case you don't have to take too much time to do it, but you see that it's a new type of problem, and so we're learning a new problem solving skill in that process. The next problem is number 321, and this comes from the winter 2017 exam. This is question paper 4, variant 1, and question number 10 from that paper. We are told that the mean value of an alternating current is 0, and we want to explain why heating occurs when there's an alternating current in a resistor. Now, we remember that alternating current changes direction, but the power that dissipates across a resistor doesn't depend on the direction. A negative current doesn't mean, not negative in the sense of a vector. Negative current simply just means switching directions. So there will be heat across a resistor, whether a current's moving in one direction or other direction. It's not going to be negative heat through a resistor if the current changes direction. So there's still heating irrespective of the direction. So how can we write this? We can say that alternating current changes direction, but the heating effect, which is what the question is asking for, or you can say the power dissipated. It's good to be able to know to use these two interchangeably. The power dissipated or the heating effect does not depend on the direction of the current. I mean, current can flow in either way. You're not going to get negative power for one and positive for another. There will still be heat going through the resistor. There will still be current going through the resistor and power produced or power dissipated in that resistor, and so heating will occur as well. You can also say, you can do it a bit more mathematically. You can also say that, well, power is proportional to I squared. Whether I have a P is equal to I squared R, if I have one resistor, a resistor, then the only thing changing is the current. Irrespective of whether current is positive or negative, power is always greater than 0. Heat is always greater than 0. So there will always be heat dissipated through a resistor, even if it's an alternating current. We're then told the transmission of electrical energy is frequently achieved using alternating high voltages, and we want to suggest why high voltages are used. So this is not so much in the current version of the syllabus, but it might be something that they expect you to recall from IGCSE O-levels. So we can say that for the same power, high voltages, and in the same case, and hence lower currents. When we have higher voltages, we can use lower currents, and those are used. And what this means is that the lower currents mean less heat is dissipated in the cables. So if the cables have a very high resistance R, and like we said above, P is proportional to I squared, if I can keep the value for I low, since I can't change the resistance of the cables, then I can keep the power low and I can keep the resistance low, the heat dissipated in those cables low. So we can, the lower the current, that means the lower the power dissipated. So high voltages allow us to use lower currents. So that's one of the reasons why we use high voltages. And we want to then state a reason why the voltage is alternating, why transmission of electrical energy from power station to substation to home uses alternating voltage. Now again, something that we didn't really learn in the new form of the A-level syllabus is that voltages can be easily stepped up, alternating voltages I should say, alternating voltages can be easily stepped up or stepped down using transformers. Another reason would be they only want one reason. Well, we could say it nonetheless. We can say it is also easier to rectify AC than it is. So it's easier to convert AC to DC than invert DC, converting DC to AC. So it's an easier process to rectify AC than it is to invert DC. That's another reason as well. And so this question was purely conceptual and was worth 6 marks. So if you remember your concepts and your theory, then you can answer this question in a fairly short space of time. And the next question is the last one we'll do for this video. It's question 323. Again, subject code for A-level physics is 9702. This comes from the March 2016 exam. It's question paper 4, variant 2, and question number 3 from that paper. And we are first asked to define specific heat capacity. So it looks like it's going to be a question on temperature mixed with some alternating currents. What is specific heat capacity? It's the thermal energy, again, per unit mass, because of the word specific, per unit mass, required to change the temperature of a substance by 1 degree Celsius or by 1 Kelvin. It's about the same. It's the thermal energy per unit mass that's required to change the temperature of a substance by 1 degree Celsius. It is a joule per kg per Kelvin, or a joule per kg per degree Celsius. We're then told that a student carries out an experiment to determine the specific heat capacity of a liquid using the apparatus as shown. Liquid enters the tube at a constant temperature of 19.5 degrees Celsius and leaves the tube at a temperature of 25.5 degrees Celsius. The mass of liquid flowing through the tube per unit time is m, and the electric power P is dissipated in the heating coil, and the student changes m and adjusts P until the final temperature of the liquid leaving the tube is 25.5 degrees Celsius. The data is shown in figure 3.2. We're given the rate of flow of liquid through the tube and the power through the tube. And we are asked first to suggest why the students obtain data for 2 values of m rather than 1 value. And that's because there's an external factor that we have to take into account. And that external factor is the heat transfer to the surroundings. So the student does this to determine the heat transfer to the surroundings. And if this doesn't make sense, it will in the next part of the question, but this is why we take multiple readings rather than one to account for the heat transfer. So we're not only accounting to the counting for the heat that is given to the liquid, but we're also counting for the heat transfer. Some of that heat energy goes to the surroundings outside the tube. And so the previous question comes in handy here because I want to find the specific heat capacity of the liquid. And so we did a question similar to this on the past exam questions on temperature, on the thermal physics, but we'll do a very similar example here. So initially, for the first set of data, the heat energy going into the liquid is Q1, which is the power times time. I'm going to call it P1 T1, and this is equal to the mass of liquid passing through the tube, M1, times the specific heat capacity, C, times delta theta 1, plus, and the thing we have to consider, H1. That's where the heat loss comes from, the heat transferred to the surroundings. For the second set of data, the second row in the table, the amount of heat energy is the new power P2 times T2, and this is equal to the mass moving through the tube, M2 times C delta theta 2, where delta theta is the change in temperature, plus the heat loss. So again, that's a different heat loss, H2. So there's a lot of unknowns in this problem. But what I can do is I can divide both sides of this equation by T, and what I get is P1 is M1C delta theta 1 by delta T plus H1 over T1. We won't call it delta T, we'll simply call it T1 in the time T1. And P2 is M2C delta theta 2 divided by T2 plus H2 over T2. Now, why would I do this? It's because the rate at which heat is lost to the surroundings is the same. H1 over T1 is equal to H2 over T2. So the rate at which the heat loss to the surroundings is the same because the temperature in the tube is the same. So liquid enters at 19.5 degrees and exits at 25.5 degrees Celsius. So the temperature is not changing between the two sets of data. So the temperature difference between the tube and the surroundings always remains the same. And remember, the rate of heat transfer depends on the temperature difference between the two objects. So I know that the rate of change of heat transfer will remain the same. So if I call the first equation 1 and I call the second equation 2, what I get is I can rearrange and subtract the second equation minus the first equation. I get P2 minus P1 is equal to C into M2 delta theta 2 minus M1 delta theta 1. That means the specific heat capacity, the thing that I want to solve, and remember the time is the same for T1 and T2, which is 15 seconds. And I can write the value for the specific heat capacity as 44.9. That's the two powers, and they're both given in watts. So 44.9 minus 33.3, and all of this divided by 1.58 times 10 to the minus 3, converting grams to kilograms, times the temperature change, which is 6 degrees. We're going from 25.5 or 19.5 to 25.5. That's 6 degrees Celsius or 6 Kelvin, minus 1.11 times 10 to the minus 3, also times 6. And so I get a specific heat capacity of 4,100 joules per kilogram per Kelvin. And so this question, very similar to the ones we covered in the thermal physics Papa Cambridge questions, requires a bit of work. You can do it quicker, obviously, but it's important for me to explain it in the most simplest way possible and build up to the solution. But you can figure out how to do this much quicker than I have. And so that was worth 3 marks. The last question says, when the heating in coil B dissipates 33.3 watts of power, the potential difference V across the coil is given by the expression V is 27 sine 395 T. We know that V is V naught sine omega T. The potential difference is measured in volts and the time is measured in seconds, and we want to determine the resistance of the coil. Okay, so we know the power, and I'm obviously going to have to relate the power to the resistance. And I also know the voltage. Now the power is the RMS voltage squared divided by the resistance, which means that it's the peak voltage squared, which is what I know, V naught is 27, divided by 2R, as we've done before. And so the resistance is the peak voltage squared, V naught squared, over 2 times the power. And the peak voltage is 27 volts squared, divided by 2 times the power, which is 33.3 watts. And what I get is 10.9 ohms. And so I can use 3 significant figures. Since all my values here are given in 3 significant figures, I have a resistance of 10.9 or 11 ohms. And so once I'm given the expression, usually things become easy. I'm given the value for omega here. I'm also given the value for V naught. So I can fully describe what the voltage is going to look like across the tube when the power is 33.3 watts. I think the most complicated question there was calculating the specific heat capacity. And the alternating currents, to be fair, only really came in the very last question. But I do think that this entire question is a good example of why it's important to understand your previous topics before you move on. Because it's always likely, always the case in the real world, where topics aren't separated. Things come together, physics, chemistry, thermodynamics, and electrical fields, and all of these things come together in order to make the real world work in the way it does. So this question in total was 9 marks, and in the next video I make, we'll go over more of the alternating currents questions, where we look at specifically the half wave and full wave rectifications and the bridges, and how to deal with the capacitors when we use them for smoothing after rectification has taken place. So I hope this video was helpful. If it was, please leave a like, comment down below, subscribe to the channel if you haven't already. But for now, that's all from me, Mr. K, and I'll see you again next time when everything is relative.